Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed upon Schrödinger's time independent and dependent equations. In this lecture video, I will discuss upon applications of Schrödinger's equations. So let's get started. The content of this lecture video is as follows. I will discuss applications of Schrödinger's equations. First, particle enclosed in infinitely deep potential well, that is particle in rigid box. And second, particle in finite potential well, that is particle in non-rigid box, qualitatively. Followed by I will discuss problem solving related to this topic. First of all, let's discuss particle in infinite potential well. If a particle is in a potential well and the total energy of the particle is less than the height of the potential well, it is considered as trapped inside the well. In classical mechanics, this particle can vibrate back and forth due to collision with walls, but cannot leave the well. In quantum mechanics, it is called as a bound state. Consider a particle is enclosed in a potential well of rigid box having infinite potential, that is V is equal to infinity, as shown in this diagram. Inside the box, motion of the particle is restricted between x is equal to 0 and x is equal to L. Assuming the collision of the particle with the walls as elastic, total energy of the particle, that is capital E, remains constant. The potential energy of the particle is infinite outside the box, that is V is equal to infinity at the region 1 and V is equal to infinity at the region 3 as shown in figure. So the potential energy of the particle is infinite outside the box and it can be considered as 0 inside the box, that is V is equal to 0, which is mentioned region 2 as shown in the diagram. Thus, the boundary conditions of potential energy are V of x is equal to infinity for x is less than and equal to 0 and x is greater than and equal to capital L. Second condition is V of x is equal to 0 for 0 is less than x and x is less than capital L. The wave function psi is associated with the particle. As particle cannot leave the box, hence its probability outside the box is 0. Thus, the boundary conditions for wave function are psi of x is equal to 0 for x is less than and equal to 0 and psi of x is equal to 0 for x is greater than and equal to capital L. Now to find out the wave function of the particle inside the box, we have to apply Schrödinger's time independent wave equation. So let's see first step, that is setting up Schrödinger's equation. Schrödinger's time independent equation we have already discussed in previous lecture is del square psi plus 2m upon h bar square into in bracket capital E minus capital V bracket complete into psi is equal to 0. Let's say this is equation number 1. Let in this equation the Laplacian operator is del square is equal to dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square. As particle is moving in one dimensional along x-axis, y and z coordinates are 0. Thus we can say that y is equal to 0 and z is equal to 0, where we can convert this Laplacian operator is as del square is equal to dabba square by dabba x square simply. Thus from equation 1, which reduced to dabba square psi by dabba x square plus 2m upon h bar square in bracket capital E minus capital V bracket complete into psi is equal to 0. Inside the box, the potential energy of the particle capital V is equal to 0, as we have already discussed earlier. Therefore, delta square psi by delta x square plus 2m upon h bar square into capital E into psi is equal to 0. Let's say this is equation number 2. Now let's assume that 2m capital E upon h bar square is equal to k square. Let's say this is equation number 3. Thus equation number 2 reduces to delta square psi by delta x square plus k square psi is equal to 0. Let's say this is equation number 4. Now let's see step number 2, that is general solution of Schrödinger's equation. Equation number 4 is a second order differential equation. Therefore, its general solution can be written as psi of x is equal to capital A into sine of kx plus capital B into cos of kx. Let's say this is equation number 5. So in this equation number 5, capital A and capital B are constants. Now let's see the boundary conditions. First is at x is equal to 0, the particle would be present on the boundary and its energy would be infinite, that is equal to the energy of the potential wave. Hence it cannot be present at x is equal to 0. And thus its wave function psi is equal to 0 at x is equal to 0. Therefore, by applying boundary conditions psi is equal to 0 for x is less than and equal to 0, we can get 0 is equal to capital A into sine of kx plus capital B into cos of kx. Therefore, this equation can be written as, by putting the value x is equal to 0, 0 is equal to capital A into sine of k of 0 plus capital B cos of k of 0. As A sine of k of 0 is equal to 0 and B cos of k of 0 is equal to 1, then we get B is equal to 0. Therefore, substituting capital B is equal to 0 in equation number 5, we get psi of x is equal to capital A into sine of kx. Let's say this is equation number 6. Now let's see the second boundary condition, that is at x is equal to capital L, as shown in the figure. The particle would be present on the boundary and its energy would be infinite, that is equal to the energy of the potential wave. Hence it cannot be present at x is equal to capital L, and thus its wave function psi is equal to 0 at x is equal to capital L. Therefore, by applying boundary conditions psi of x is equal to 0 for x is greater than and equal to capital L, we get psi of x is equal to 0 at x is equal to capital L. Therefore, substituting this value in equation number 6, we get 0 is equal to capital A into sine of k of capital L. As capital A is not equal to 0, since psi will be become 0, thus a sine of k of capital L is equal to 0. Therefore, above equation implies that k capital L is equal to n pi, where small n is the integer and which is n is not equal to 0. This equation is known as quantization condition. Therefore, in quantization equation, k capital A is equal to n pi, where n is equal to 1, 2, 3 and n is not equal to 0, as it may lead to either two conditions. Capital L is equal to 0, as capital L is the width of the box and the box capital L cannot be 0. And second condition is k is equal to 0, as k depends on the total energy capital E of the system. Therefore, k cannot be 0. So let's see the step number 3, that is energy of the particle inside the box. We have equation k is equal to n pi upon capital L. So let's square on both sides. We get k square is equal to n square pi square upon capital L square. So therefore, from equation number 3, we can write 2m capital E upon h bar square is equal to, simply by putting the value of k square, we can write is equal to n square pi square upon capital L square. So simply by rearranging this equation, capital E, that is the energy of the particle inside the box, capital E is equal to n square pi square h bar square divided by 2m capital L square. Now as small n is an integer, that is energy varies as per the values of small n, the Servo equation can be written as capital E subscript small n is equal to small n square pi square h bar square divided by 2m capital L square. As we know that h bar is nothing but is equal to h upon 2 pi. Therefore, we can write this equation capital E subscript small n is equal to small n square pi square in bracket h upon 2 pi bracket complete bracket square divided by 2m capital L square. Thus the energy of the particle inside the box can be written as capital E subscript small n is equal to small n square h square divided by 8m capital L square. Let's say this is equation number 7, where in this equation small n is an integer, but here n is not equal to 0 and n's values are 1, 2, 3 and so on. Now let's see the energy levels of the particle inside the box. As small n is integer from above, it is clear that the particle inside an infinite potential well can have only certain discrete values of energies. However, the minimum value of energy can never be 0 as n is not equal to 0. Therefore, as shown in this diagram, you can see on the y-axis is the energy and the values for n is equal to 1, we have h square upon 8ml square. Simply by putting the value of small n, for the n is equal to 2, we have 4h square upon 8ml square. For n is equal to 3, 9h square upon 8ml square. These values of energies are known as energy eigenvalues. So all these values are very important as far as the energy of the particle inside the infinite potential well is concerned. As shown in this diagram, energy values E1, E2, E3 and E4 are the energy states, whereas K1, K2, K3 and K4 are the wave numbers. These are the corresponding wave numbers to the energy values or the energy states. Therefore, the energy of a particle in a box shown in yellow circle in the diagram and the free particle, that is the red line as shown in this diagram, both depend upon wave number in the same way. However, the particle in a box may only have certain, that is the discrete energy levels. Now this is about the energy states and the corresponding wave numbers for the particle inside the potential well. Now let's find out the wave function of a particle inside the box. Now from equation number 6, the wave function psi of the particle inside the rigid box is given by psi of x is equal to capital A into sine of kx. In this equation, k capital L is equal to n pi, where n is equal to 1, 2, 3 and so on, and n is not equal to 0, as it may lead to either k is equal to small n pi upon capital L. So by simply putting the value of k in this above equation, we can write psi of x is equal to capital A into sine of small n pi upon capital L into x. Let's say this is equation number 8. Thus for each energy value capital E subscript small n, there is a wave function psi subscript small n which is known as an Eigen Function. The particle can be found at any location inside the box. It means its probability of finding inside the box is 1. Thus the wave function psi n should satisfy normalization condition That is the probability that the particle can be found in the region between x is equal to 0 and x is equal to L is 1. As we have the equation psi of x is equal to capital A into sine of kx, let's integrate this equation with the limit x is equal to 0 and x is equal to L. Therefore, above equation we can draw it. Integration with limit x is equal to 0 to x is equal to capital L, psi n mod square dx is equal to 1. Therefore, integration with limits x is equal to 0 to x is equal to capital L, capital A square into sine square in bracket small n pi x upon capital L bracket complete into dx is equal to 1 by simply putting the value of psi of x in this integration. Therefore, after integrating, we can write capital A square with integration x is equal to 0 to x is equal to L, these are the limits, into sine square into in bracket n pi x upon capital L bracket complete into dx is equal to 1. Therefore, by using sine square theta is equal to half in bracket 1 minus cos 2 theta. Therefore, we can write capital A square divided by 2 integration with limit x is equal to 0 to x is equal to L in bracket 1 minus cos of 2n pi x divided by capital L bracket complete dx is equal to 1. Therefore, capital A square divided by 2 integration with limits x is equal to 0 to x is equal to L in bracket dx minus cos of 2n pi x divided by capital L into dx is equal to 1. So this is simply by multiplying dx inside the every term inside the bracket. Therefore, we can write capital A square divided by 2 in square bracket integration with limits x is equal to 0 to x is equal to L dx minus integration with limits x is equal to 0 to x is equal to capital L into cos of 2n pi x upon capital L into dx. So simply by separating the integrations. So square bracket complete is equal to 1. Therefore, capital A square divided by 2 in square bracket x minus capital L upon 2 pi n into sine of 2 pi n x divided by capital L square bracket complete limits from 0 to capital L is equal to 1. So simply solving this equation, we can write capital A square divided by 2 in square bracket by separating the limits capital L minus capital L upon 2 pi n into sine of 2 pi n capital L divided by capital L minus in bracket 0 minus capital L upon 2 pi n into sine of 2 pi n into 0 divided by capital L bracket complete square bracket complete is equal to 1. As we know that sine 2 pi n is equal to 1 and sine 0 is equal to 0. So above equation simply we can simplify it as capital A square divided by 2 into capital L is equal to 1. So therefore, rearranging this equation we can write capital A is equal to under root of 2 upon capital L. Let's say this is equation number 9. Substituting the value of A, that is equation number 9, in equation number 8, we can write the wave function equation psi of x is equal to under root of 2 upon capital L into sine of small n pi x upon capital L. This is equation number 10. This equation number 10 represents the wave function psi of the particle enclosed in rigid box of length capital L. As psi gives negative probability density, that is psi mod square, determines the position of the particle inside the box. The wave function psi and the probability density psi mod square of the particle psi can be plotted as shown in this diagram. In this diagram, wave function and probability functions are shown. The locations where the probability densities show peaks are the most probable position of the particle. So according to the classical mechanics, A particle with any energy can be present at any location inside the box. The quantum mechanically probability of the particle being present in the box is different according to the quantum mechanics or the quantum number small n. Therefore, for example, if at small n is equal to 1, then psi mod square, that is the probability of finding the particle, is maximum at L by 2, that is at the center of the box. Similarly, at n is equal to 2, that is psi mod square, that is the probability of finding the particle is maximum at L by 4, and L is equal to 3L by 4 as shown in this diagram. Now let's see the animation diagram of the particle in infinite potential well. Here are the total A to F panes are shown. The trajectories of a particle in a box, also called a infinite square well, in classical mechanics as shown in pane A, and quantum mechanics for the pane B to F. In A, the particle moves at constant velocity, bouncing back and forth. Whereas in pane B to F, wave function solutions to the time-dependent Schrödinger equation are shown for the same geometry and potential. The horizontal axis is position, whereas the vertical axis is the real part shown in blue color line, or imaginary part shown in red line of the wave function. In pane B, C, D are stationary states, that is the energy eigenstates, which come from solutions to the time-independent Schrödinger's equation. In pane E and F are non-stationary states, solutions to the time-dependent but not for the time-independent Schrödinger equations. Both pane E and pane F are randomly generated superpositions of the 4 lowest energy eigenstates. Now let's see the diagram for higher dimensional boxes. If a particle is trapped in 2-dimensional box and it may freely move in the x and y directions between the barriers separated by the length, let's say capital Lx and capital Ly respectively. For a centered box, the position wave function may be written including the length of the box as psi of x t capital L. Using similar approach to that of the one-dimensional box, it can be shown that the wave functions and energies of centered box are given by psi n x and y is equal to psi n x of x t lx into psi ny of y t ly. Therefore, energy we can write the energy equation. Capital E of nx and y is equal to h bar square k square of nx and y divided by 2m, where the two-dimensional wave vector is given by knx and y is equal to knx x cap plus kny y cap is equal to nx pi upon lx x cap plus ny pi upon ly y cap. Therefore, the wave function of a two-dimensional well with nx is equal to 4 and ny is equal to 4 is shown in this diagram, which is the higher dimensional boxes. So this is all about particle in infinite potential well. Now let's see the particle in finite potential well. In real situations, potential energies are never infinite and potential barriers of finite height exist. Consider a particle is enclosed in a potential well of energy V0 with width capital L. Consider the energy of particle capital E is less than V0. Classically, the particle strikes the walls of the well. It is reflected and cannot enter region 1 and region 3 as shown in this diagram. It is possible for the particle to have energy that exceeds V0. So the particle can exit outside the box and the wave function psi of the particle will not be 0 at the boundaries of the box. We can use the Schrödinger's time-independent equation to find the wave function of the particle inside and on the boundaries of the box. As shown in figure, consider a particle is enclosed in a potential well of rigid box having finite potential V is equal to 0, that is in the region 2. Inside the box, motion of the particle is restricted between x is equal to 0 and x is equal to capital L, that is the length of the box or length of the well. The potential energy of the particle is V is equal to V0 outside the box, and it can be considered V is equal to 0 inside the box. Therefore, assuming the collision of the particle with walls as elastic, total energy of the particle, that is capital E, can be exceed V0. Following conclusions can be drawn by solving Schrödinger's equation for finite potential well. The wave functions are similar to those of infinite well. However, at the boundary, wave function is not zero and it is also extend a little outside the box. It means probability of particle penetrating through the wall is not zero. Therefore, even though the particle energy capital E is less than the potential energy capital V, there is a definite probability that the particle is found outside the box. The wave function and the probability function both are shown in this diagram. Very similar wave function nature and the probability function is similar to the particle in infinite potential well. Whereas in this case, the probability function and the wave functions extends into the forbidden region as shown in this figure. So therefore, the possibility or the probability of finding the particle at the center of the potential well is maximum, that is at the location L by 2, whereas it extends towards the forbidden region. This is the main difference of particle in finite potential well and particle in an infinite potential well. So this is all about the particle in the both potential wells. Now let's discuss few problem solving related to this topic. Problem number 1. Find the probability that a particle trapped in a box capital L void can be found between 0.45 capital L and 0.55 capital L for the ground state and first excited state. Therefore, the solution for this problem is as follows. We have formula psi of x is equal to under root of 2 upon capital L into sine of n pi x upon capital L. So above equation can be written as the probability, that is P, capital P, is equal to 2 upon L integration with limits x1 to x2 sine square in bracket n pi x upon capital L bracket complete into dx. Therefore, this equation can be written as 1 upon L integration x1 to x2 in bracket 1 minus cos of n pi x upon L bracket complete into dx. So applying the integration to this term, we can write P is equal to 1 upon L in square bracket x with limits x2 to x1 minus 1 upon 2 n pi in square bracket sine of 2 n pi x upon capital L square bracket complete with limits x2 to x1. Therefore, capital P, that is probability, is equal to 1 upon capital L in square bracket x2 minus x1 minus 1 upon 2 n pi in square bracket sine of 2 n pi x2 upon capital L minus sine of 2 n pi x1 upon capital L square bracket complete. For ground state, small n is equal to 1, hence above equation can be written as capital P is equal to 1 upon capital L in square bracket as per the given values 0.55 capital L minus 0.45 capital L. These are the values of x2 and x1. So square bracket complete minus 1 upon 2 pi in square bracket sine of 2 into 180 degree into 0.55 L upon capital L minus sine of 2 into 180 degree into 0.45 capital L upon capital L square bracket complete. So after solving this, we get P is equal to 0.1 minus 1 upon 2 into 3.143 in bracket minus 0.309 minus 0.309. So after solving this, we get the value P is equal to 0.198. So for first excited state, that is n is equal to 2, hence above equation can be written as P is equal to 1 upon capital L in square bracket 0.55 capital L minus 0.45 capital L bracket complete minus 1 upon 4 pi in square bracket sine of 4 into 180 degree into 0.55 L upon capital L minus sine of 4 into 180 degree into 0.45 L upon capital L bracket complete. So after solving this, capital P, that is probability, is equal to 0.1 minus 1 upon 4 into 3.143 in bracket 0.5878 minus 0.5878. So that is equal to 0.0065. So these are the two values for the probability to find out the particle at ground state, that is P is equal to 0.198, whereas first excited state is 0.065. So this is the solution of problem number 1. Let's see problem number 2. Find the lower energy of an electron confined to move in a one-dimensional box of length 1 angstrom unit. Express the result in electron volt. So the solution for this problem is as follows. The energy value of electron in one-dimensional box are given by one equation, that is En is equal to n square h square upon atml square. This equation we have already seen before. Therefore, for the lowest energy level, small n is equal to 1. So by simply putting the values in this formula, we can write E1 as n is equal to 1. So E1 is equal to 1 square in bracket Planck's constant, that is 6.626 into 10 raised to minus 34 joule seconds, bracket complete, bracket square, divided by 8 into mass of an electron, that is 9.11 into 10 raised to minus 31 kilogram, into the length of the box, that is 1 angstrom unit is given. 1 angstrom unit is nothing but the 10 raised to minus 10 of meter. So we can write 10 raised to 10 raised to minus 10 of meter, bracket square. So after solving this, we can write E1 is equal to 6 into 10 raised to minus 18. So this is in joule. So let's convert this value in electron volt. So E1 is equal to 6 into 10 raised to minus 18 joule divided by 1.6 into 10 raised to minus 19. So therefore, that is the electron volt. We can get E1 is equal to 37.5 electron volt. So this is the solution of problem number 2. Now let's see problem number 3. An electron is confined to move in a one-dimensional potential well of length 5 angstrom unit. Find the quantized energy values for the 3 lowest energy states. Express the result in electron volts. So the solution for this problem is as follows. The quantized energy values of electron in one-dimensional potential well are given by the formula En is equal to n square h square upon atml square. So therefore, for the ground state, n is equal to 1. So E1 is equal to 1 square h square upon atml square. So that is equal to h square upon atml square, that is 1 square is equal to 1. So by simply putting the values in this formula, Planck's constant, that is 6.626 into 10 raised to minus 34 joule second square divided by 8 into mass of an electron, that is 9.11 into 10 raised to minus 31 kilogram, into length is given, that is 5 angstrom units. So 5 into 10 raised to minus 10 of meter, bracket square. So after solving this, we will get E1 is equal to 2.41 into 10 raised to minus 19 of joule. So after converting it into electron volt, simply by dividing the Coulomb's value, 1.5 electron volt, we will get this is the energy in electron volt for the ground state, that is n is equal to 1. Therefore, for the first excited state at n is equal to 2, we can write E2 is equal to 2 square h square upon atml square, where n is equal to 2. So we can write 4h square upon atml square, that is nothing but 4 times the value of ground state, that is 4 into E1. So 4 into 1.5 electron volt, so we will get 6 electron volts. So this is the energy of first excited state, that is the n is equal to 2. Next one is energy for second excited state, that is n is equal to 3. So we can write E3 is equal to 3 square h square upon atom L square. So 3 square is nothing but the 9, so 9h square upon atom L square. So 9 into the value of ground state, that is n is equal to 1, so E1. So 9 into E1, that is equal to 9 into 1.5 electron volt. So we get the value E3 is equal to 13.5 electron volts. So after the calculating all these values, we have final values. E1 is equal to 1.4 electron volt, that is the ground state. E2 is equal to 6 electron volt, that is first excited state. And E3 is equal to 13.5 electron volt, which is a second excited state. So this is the solution of problem number 3. This is all about particle enclosed in infinitely deep potential veil, particle in rigid box, and particle in finite potential veil, that is particle in non-rigid box. In my next lecture video, I will discuss about tunneling effect and its applications, which are scanning tunneling microscope, tunneling diode, alpha decay, and quantum computing. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.